Good afternoon, everyone. I hope everybody's doing good today. Happy Friday. We're looking at finishing off today our lesson on graphing functions. So what we're going to do today is another example where we take the entirety of our knowledge about the function, everything from asymptotes and symmetry and intercepts, all the way up to the first derivative and the second derivative and what they tell us about the graph. We're going to take all of that knowledge and put it together to come up with a picture of what the graph looks like. So the function we are looking at today is y is equal to x multiplied by x squared minus 1 raised to the 2/3. Again, there is that graphing summary document that I created for you. It's a good idea to have some kind of summary of things. Whether you want to use that or not is up to you. Just like on Wednesday's lesson, I have already determined the derivative and the second derivative. This would be an hour-and-a-half long video if we had to determine the derivatives as well. So they're there for us for our reference. The domain is any real number. The reason why the domain is x is any real number is there are no restrictions in the function. There's no denominators that would cause non-permissible values. There are no radicals that would cause non-permissible values. So we don't have to worry about any special domain. The y-intercept and the x-intercept would be found by looking at the function and following the rules that we have for x and y-intercepts. The function is y equals x multiplied by x squared minus 1 to the, I think it said 2/3. For an x-intercept, you let y equal 0. So this becomes 0 equals x multiplied by x squared minus 1 to the 2/3. By inspection, you can see that x equals 0 is a solution and plus or minus 1 is a solution. At this stage, certainly when we look at x squared minus 1, you should be seeing x plus 1, x minus 1. To find a y-intercept, you let x equal 0. So the y-intercept will be equal to 0 multiplied by 0 squared minus 1 to the 2/3, which is 0, which shouldn't come as a surprise to you because whenever you have an x-intercept of 0, that's going to land on the origin, which is where the y-intercept is. We can add that information to our list. The x-intercept of -1, of 0, and of +1 are now added, and the y-intercept of 0 is added. There are no asymptotes of any kind, very similar to the example we looked at on Wednesday. Asymptotes are only possible if you have a rational function, which means you need a denominator that's a function of x, and there is no denominator here. Symmetry is found by determining what f of -x is. Well, f of x is x multiplied by x squared minus 1 to the 2/3. So we're going to replace x in the original function with -x. And I get f of -x equals -1x multiplied by x squared minus 1 to the 2/3. When I square the -x in the brackets, it becomes +x squared. And since x multiplied by x squared minus 1 to the 2/3 is f of x, f of -x is equal to -1 multiplied by f of +x, and that is the textbook definition of an odd function. So the symmetry is odd. Now we're going to do the first derivative chart, and we're also going to do the second derivative chart. Looking at the first derivative, we can see there are a number of critical numbers. In the denominator, we have x equals -1 and x equals +1. In the numerator, 7x squared minus 3 equals 0 leads us to critical values of x, which would be 7x squared equals 3, which means x squared equals 3/7, or x equals plus or minus root 3/7. And at this level, we have neither the time nor the motivation to worry about rationalizing root 3 over 7. I don't care. It's just the numbers. So we also have positive root 3/7 and negative root 3/7. To build our first derivative chart, you need to be able to put these numbers into numerical order. So at some point we're going to evaluate what the square root of 3 over 7 is anyway for our graph. We might as well do so now so we get a handle on what that number is in decimal form, approximately. It's approximately 0.655. What that means is that if we were to put these 4 critical values of x on a number line, -1 would be the smallest. So we would have -1, then we have negative root 3/7, then we have positive root 3/7, and then we have positive 1. I don't care if this is scaled properly. All I'm interested in is the order of these. So what that tells us is we are going to have 4 critical values cutting our domain into 5 pieces. We're going to have a domain from -infinity to -1. We will have a domain in between -1 and negative root 3/7, in between negative root 3/7 and positive root 3/7, in between positive root 3/7 and 1, and from 1 to infinity. So I'm going to start building the first derivative table now. We said we would go from -infinity to -1, from -1 to the negative of the square root of 3/7, from the negative of the square root of 3/7 to the positive of the square root of 3/7, from the positive of the square root of 3/7 to 1, and from 1 to infinity. What do we put across the top? Well, we put all of the pieces of the derivative across the top. When I take a look at the derivative, there is a 7x squared minus 3 on the top. Now that is a quadratic factor and it's not factorable. You could certainly factor it by introducing radicals, but I don't think that's a good idea. I think it's better just to put that entire thing on the top of our first derivative chart. So we have 7x squared minus 3. We also have the number on the bottom 3, and then we have x plus 1 raised to the third and x minus 1 raised to the third. What we actually have is x squared minus 1 raised to the third, but if we factor it, that's what we get. The 3, which is on the bottom, really doesn't make any difference because it's a positive number, but I chose to include it, and I would probably include the 3 for explanation purposes with the x plus 1 to the third. Let's deal with the x plus 1 to the third. X plus 1 is going to be negative all the way up to -1, and when we take the cube root of a negative, we get a negative. Once we pass -1 for x, x plus 1 becomes positive, which means the cube root of it is going to become positive. X minus 1 will be negative in between -infinity and -1, and if it's negative, the cube root is negative. And the same argument is going to hold water until we get past 1. Once we get past 1, x minus 1 will be positive, so the cube root will be positive. Now this whole bit of business about a factor being negative and then changing to positive is not going to be valid for the 7x squared minus 3. And the reason is it's quadratic, and quadratic expressions change direction. They go from maybe being negative to negative, or from being positive to positive. So I would recommend actually putting in a number for x, taking your calculator and say for the first interval, using x equals negative 100. Now I'm choosing negative 100 because I don't think we really need a calculator. When I square negative 100, I get a large positive number. Times 7 is still large and positive, minus 3 will still be positive. And you will discover if you do that for the following intervals, you will get positive. It is only in between negative root 3/7 and positive root 3/7 that you are going to get a negative. But feel free to use your calculator and try that. Don't forget we are doing this so we can determine whether the derivative dy dx is positive or negative. So we multiply all of the signs together, we get positive, then we get negative, then we get positive, and we get negative, and we get positive, which tells us in the first interval the function is increasing, then it's decreasing, then it's increasing, then it's decreasing, then it's increasing. So we have a number of extreme points on the graph. We have a maximum at negative 1, a minimum at negative root 3/7, a maximum at positive root 3/7, and a minimum at 1. So we can go ahead and start compiling that information in our summary. We have a maximum at negative 1, and we also have a maximum at, I believe it was positive root 3/7. We have a minimum at the negative of the square root of 3/7, and we also have a minimum at positive 1. All right, and we'll worry a little bit later about what those y-coordinates are. We are going to need to know the y-coordinates of those maxima and minima points so that we can plot them accurately on the graph. In the meantime, though, let's do our second derivative chart, which means we have to look at the second derivative, and man, oh man, do we ever have a lot of critical points here. We are going to have the following numbers for critical points. We're going to have plus or minus 1 again, because the denominator contains x plus 1, x minus 1. We're going to have a critical value of x for the second derivative of 0, because there's a factor of x in the numerator. And then we're also going to have plus or minus the square root of 9 over 7. And the square root of 9 over 7 is greater than 1. Again, I'm not drawing this to scale. All I'm doing is putting them in order. So we are going to have to go from negative infinity all the way to, but not including, negative root 9/7. We will have to look between negative root 9/7 and negative 1, between negative 1 and 0, between 0 and 1, between 1 and root 9/7, and finally from root 9/7 up to positive infinity. So we have a whopping 2, 4, 6 intervals. All right, so let's build this chart now. Here we go. We are going from negative infinity to the negative of the square root of 9/7, from the negative of the square root of 9/7 to negative 1, from negative 1 to 0, from 0 to 1, from 1 to the positive of the square root of 9 over 7, and from the positive of the square root of 9/7 to infinity. Now, I wrote all of those down by delving into my memory for the numbers. I'd better just make sure that is right. I'm pretty sure it's right, but I want to go back one page and just look. Negative infinity to negative root 9/7, negative root 9/7 to negative 1, negative 1 to 0, 0 to 1, then to root 9/7, then to infinity, it's good. Now across the top, we have to put all of the factors of the derivative. So we have 4x, 7x squared minus 9, then we also have 9 multiplied by x squared minus 1 to the 4/3. We're doing this so we can determine the nature of the second derivative. And we're doing that so we can determine the concavity of the function. And we're doing that so that we can identify any inflection points. I'm not going to worry about the x squared minus 1 being factored out because the x squared minus 1 is raised to the 4/3. That 4 is going to take any negatives and make them positive. So 9 times x squared minus 1 raised to the 4/3 is positive in all of those intervals. 4x will be negative whenever x is negative, and then when x becomes positive, 4x will become positive. Same kind of thing we had to grapple with the first derivative. 7x squared minus 9 is a quadratic expression. So what you need to do is put in numbers for x in the intervals. Now I will show you a little trick on why I know it's positive here and negative everywhere else. What I'm doing is, in my mind, I'm looking at the graph of y equals 7x squared minus 9. Well, I know the two x-intercepts will be the negative square root of 9/7 and the positive square root of 9/7. And I know that since the leading coefficient of this quadratic function is positive, this is a parabola that opens up. If I were to sketch y equals 7x squared minus 9, it would look like this, which tells me that everywhere to the left of negative 9/7 for x, the function is positive. And everywhere to the right of the square root of 9/7, the function is positive. And everywhere in between, the function is negative. So there are certain tricks you can use here to fill out the chart. Now let's take a look at what that tells us about the derivative. Rather, the second derivative, we multiply the signs and get negative, then positive, then it's still positive, then it becomes negative, it's still negative, and then it becomes positive. So we have a boatload of inflection points because the graph is concave down, then concave up, then it goes to concave down, then it goes back to concave up. We have an inflection point at negative root 9/7, comma, some number. We have an inflection point at the origin. We've already established that when x is 0, y is 0. And we have an inflection point at positive root 9/7, comma, some y coordinate. Now what we're going to do is put those 3 points into our summary table. So we have an inflection point at negative root 9/7, comma, some number. We have an inflection point at 0, comma, 0. And we have an inflection point at positive root 9/7, comma, some number. Now, because we're not too interested in exact values, but instead what we are interested in is what the graph looks like, we're going to find all of our y coordinates here by cheating a little bit and using the tabular features of our graphing calculator. I'm going to warn you, though, that we do not want to look at the graph of the function. You don't want to cheat. So I am going to put in for y1 the function, which is x multiplied by x squared minus 1. And that's raised to, in brackets, 2 over 3. We don't want to peek at the graph. We want to go to the table. So I'm going to go second window to get to table setup and set it so that the independent variable is being asked for. That means I have to enter the x's. And when I go to my table now, I'm going to enter x equals -1 so that I can see what the y coordinate is. Well, the y coordinate there is 0. I'm going to enter the square root of 3 divided by 7. And I get a y coordinate of approximately 0.45. It's just an approximation. We're not going to worry about the exact value. Since the function was odd, when I enter the negative of the square root of 3 over 7, I'm going to get the negative of what I got before. So we have about 0.45, about -0.45. Of course, when we put 1 in for x, we're going to get 0. So I'm going to fill in these numbers now. 0, positive 0.45, negative 0.45, and 0. And now we have to find the inflection points. So what do I get for y when I use for x the square root of 9 divided by 7? I get approximately negative 0.49. I'm just going to call that negative 0.5. And we're going to get positive 0.5 over here because the function is odd. But if you need to be convinced of that, when I put in the positive of the square root of 9 over 7, I get positive 0.49. So now we have to sketch this. And what I'm going to do when I set up my horizontal axis is I'm going to be looking at all of these x coordinates that are important. If I were to, right now, before I go to my grid, start putting all of these x coordinates that are important on a number line, 0 is clearly an important x coordinate because something happens at 0. There's an inflection point. 1 is clearly an important x coordinate, so is -1. So we're going to have to go at least over to -1 on the left and over to +1 on the right. Something happens at the square root of 3/7. Well, the square root of 3/7 was about 0.65. So 0.65 is already included in this domain that I'm drawing down at the bottom of the page. Something else happens at the square root of 9 over 7, which is a little bit bigger than 1. The square root of 9 over 7 is 1.1. That means that something important is going to happen over here, to the right of 1 at the square root of 9/7 and to the left of -1. So I'm thinking that I should probably scale my horizontal axis so that I go from about -2 to +2. That's kind of the first step, is to look at all of your x values. Look at all of these because something crucial happens at all of these x values. And if something crucial happens at all of those x values, then you need to scale your axis to show all of those values. So now I'm going to go to my grid, and I said that we wanted to go from about -2 to 2. Again, I think we want to do a presentable job with this, so we would like to use a ruler to scale this. I'm just looking at the numbers and thinking here, and I think if you're going to have to make your own decision, but I think if I put a 1 here, which is 4.5 centimeters from the origin, another 4.5, 1, 2, 3, 4.5 would take me here. On the other side, this would be -1, and this would be -2. So that is what I'm going to use for my scale horizontally. Now what I'm going to have to do is go back and look at all of the y coordinates to decide how I'm going to scale this vertically. What are my y coordinates of all these interesting points? Well, they're all pretty small. We've got y coordinates of positive 0.45 and positive 0.5. We don't have any really big y coordinates, so I'm thinking here if we go from -1 to 1 for y, we'll be fine. Again, you want to do a fairly decent job of scaling this. I'm not going to move my ruler around. I'm just going to use that to decide that this is -1. We're not done by any means. We have a number of things to do now. One of them is to plot the points that we have the coordinates for. The other is to identify where things are concave up, where things are concave down, where things are increasing, where things are decreasing. And then the most challenging part is at the end of all this to try to figure out what the graph looks like. So we know that the graph passes through the origin. We also happen to know that that's an inflection point, but I'm really not too concerned about that. What else do we know? Well, if I flip back and I take a look at -1, 0 and 1, 0, those are points on the graph. And they are also points that correspond to max-min values. Let's keep that in mind. I don't know how much I want to clutter things up, and I don't know how much you want to clutter things up, but there is a maximum at this point. There was a maximum at -1, 0, and there is a minimum at this point, 1, 0. We can also put in the square root of 3/7, 0.45. The square root of 3/7 was about 0.65. So we're plotting now for this other maximum about 0.65, 0.45. 0.65, 0.45. I would judge 0.65, 0.45 to be about here. Now, it's not important that you get that exact. And the reason it doesn't have to be exact is all that's important is that you plot the odd point that goes with that, the one that's at -0.65, -0.45, in a symmetrical way. And what you can do is take your ruler and measure the distance from here to here, and then essentially measure that exact same distance on the other side of the origin. In other words, if this is perfectly odd in terms of symmetry, then your other point should be over here. Now again, we'll just double check that one point, which is the square root of 3/7, 0.45, is a maximum. So again, I'm not sure how much you want to really clutter things up here, but we can write minimum. by this point, and maximum by this point. What else do we have? We have an inflection point. Well, we have the inflection point at the origin, but we also have one at a little bit more than 1, comma, 0.5. I'm looking right now, everybody, at this point. A little bit more than 1, comma, 0.5, we have an inflection point. So here is 1. A little bit more than 1 is a bit to the right of it. And then we have comma 0.5. And what's important here is this 0.5 is a little bit more than the 0.45. That's going to be important. If you don't put this point a little bit higher than the 0.45, you will not be successful in drawing this properly. And then we have the same odd point on the other side. And again, if you choose to, you can use a ruler to get a pretty decent picture of where that point should lie. If I extend this the same distance in the same direction past the origin, I will get the location of that other point. Now, anybody could connect the dots here and get a shape, but we want to make sure that we draw it properly, meaning all of the concavity and all of the intervals of increase and decrease match up. Now, don't forget, I'm just going to use IP for inflection point, that this is an inflection point, and the origin is an inflection point, and this is an inflection point. So now we have all the points labeled. What I'm going to do across the top is mark off the critical points of the first derivative. When you go back and you look at your first derivative chart had critical points of -1, negative root 3/7, positive root 3/7, and positive 1. So I'm going to mark those points off across the top. -1, and you don't need to draw these lines, I'm just indicating that these were all critical points. Negative root 3/7, positive 1, and positive root 3/7. These were all critical for our first derivative. And if you look at the first derivative chart, we had, I'm looking at the right-hand side here, increasing, decreasing, increasing, decreasing, increasing. So it started off increasing and it oscillated back and forth between the two, which means that the function was increasing everywhere up to this first critical value of the first derivative, then it decreased, then it increased, then it decreased, and then it increased. If I were to do the same kind of thing with my second derivative, I had a boatload of critical points for the second derivative. I had negative root 9/7, negative 1, 0, 1, positive root 9/7. So I'm going to mark off those. Negative root 9/7, negative 1, 0, positive root 5/7, and positive 1. And those red lines are telling me where things might have changed when I looked at my second derivative. What we discovered with the second derivative, concave down, then up, up, down, down, up. So the first interval is concave down. Then the next two intervals, I'm looking at the red lines here, were up and up. The next two were down and down. And then it was up again. So now our job is to graph this. And I'm going to challenge you here to pause the video and see if you can come up with how you could conceivably graph this function so that it matches all of the behavior we have at the top of the page. The only way it can happen, and I'm going to choose to use black for the color here, is if it's concave down and increasing in the first interval and then increases still, but is concave up, is if the graph looks like this, and it's very subtle. That's what the graph looks like for the first interval in terms of increasing. Now then, it decreases up to the next point, which is a minimum, and it's concave up. And it continues to be concave up, but now it's increasing to this point. And we've got half of the graph right now. The next part is concave down while it increases and then decreases. Then it is concave down while it increases and then concave up. And again, this concave up and this concave down is very, very subtle. So that's what the function looks like. Now I happen to have a graph of the function already loaded up here, and I can show it to you. It's right there. I'm going to move this around a little bit to show something to you. I'm going to pick on the side that is over here, and I'm going to highlight some key points for you. This is clearly an inflection point because you can see that it changes concavity from being concave up on the left to being concave up on the right. This is clearly a maximum. The maximum coordinates there were the square root of 3/7, and the y coordinate was, I don't remember exactly what it was, but it was approximately 0.45. And that's a maximum. There is a minimum point at 1, 0, that matched. And then at the square root of 9/7, which we said was about here, there was an inflection point. And if you look very carefully, this is concave up, but this part is concave down. These questions are a lot of work. And it isn't so much, just to let you know, it isn't so much that your mathematical career hinges on your ability to get all of these questions right, because it doesn't. What these questions are doing for you, and we've talked about this before, is they are making you into a more proficient math person. You're getting better and better and better at math every time you do more math. If you take a look at what we graphed and what I just showed you, it's not bad. It's pretty good. And if you think about the power of what we did here, that's pretty amazing that we were able to come up with this visual of the graph without using any kind of technology other than the calculator just to calculate some numbers. You can see what the assignment is. It's just the same stuff you were working on from Wednesday's lesson. You're going to pick one function and give it a shot. You're going to pick maybe a second function and give it a shot. It's entirely up to you. So I hope that makes sense. Have a great rest of the day, you guys. We'll talk to you later.